Next, we need to find out, does this orthogonal basis V1, V2, and V3 are the actual solution to the matrix from the beginning. One more time, we want to show that these orthogonal bases V1, V2, V3 are the real solution to this matrix A. Okay, so now we need to do QR factorizations. So we have to find a matrix for Q, a matrix for R. So the first thing we need to do is normalize each of these bases. Okay, so to do that, we need to find the distance or magnitude. So magnitude means distance. So we need to find the distance for V1, V2, V3. All you have to do is just square each of the number in its vector, add them up, square root, and it comes out to be 2 square root 5. So 3 squared gives me 9, 1 squared gives me 1, negative 1 squared gives me this positive 1, 3 times 3 gives me 9. So pretty much you're just squaring these numbers, add them all up, square root, and if you can, simplify it down, so it comes out to be 2 square root 5. So same thing, find the magnitude of V2. Again, magnitude means distance. So same thing, square each of these numbers, add them all up, square root, simplify 2 square root 5. Repeat that again for V3. So square each number in V3, add them all up, square root, and then simplify. Note what I have over on the right hand side. Each of these magnitude or distance are not always the same. Is the only reason why it's same, and same here. All three of these are the same. Because it's just this example. Okay, be very careful. This right here, this right here, and this right here are never the same. Okay, so be very careful. It's just the same here because it's in this example. So this could be different. This, and this could be different. Okay, so be very careful. Not all of them are the same. Okay, so be very careful. Again, magnitude is the distance for V1, V2, and V3. Just square all these numbers, add them all up, square root, simplify. Okay, now the actual normalize is this. You have to take V1, divide by the magnitude. Okay, one more time. The real normalize is take V1, divide its magnitude. Okay, so V1 divide by the magnitude of V1. Okay, so just 3. So what I have here, 3 divide by 2 square root 5, which is here. 1 divide 2 square root 5, which is here. And you go all the way through. Okay, so this is the magnitude of V1. This is the magnitude of V2. This is the normalize of V1. This is the normalize of V2. This is the normalize of V3. Okay, so be very careful. Again, this is the magnitude. Magnitude is just the distance of each of these vectors. Normalize is you will take the vector, divide by its magnitude. Okay, so this right here is the normalize of V1, normalize of V2, normalize of V3, and you put them together and it will come out to be this Q right here. So this is Q that I just found out, okay, from normalize its vector. So this is vector 1, vector 2, vector 3, and Q is the normalized vector. Okay, now we have Q, so now we need to do R. So to do R, we will follow this formula. A equal QR. I want R by itself, so bring Q over. So to bring Q over, I will transpose. So this T means transpose. So when you transpose something, you're just changing column to row. Again, one more time. We already have Q. We want to know R. So bring Q over to the other side. And when I bring it over, it will become transpose. Okay, so transpose means this. So here's our Q. So this is our Q. Okay, all we're doing is this. Taking the columns. When you transpose something, all you're doing is taking the column and rewrite it as a row. That's what transpose means. Take the column, write it as row. Take this column and write it as row. Take the third column and write it as row. Okay, so that's what QT stands for, is transpose. So that T means transpose. So one more time, you're just taking the column 1, write it as row 1. Column 2, write it as row 2. Column 3, write it as row 3. Okay, so again, T stands for transpose, and all it does is just rewriting columns into row. One more time. Column 1, change it to row 1. Column 2, change it to row 2. Column 3, change it to row 3. That's all you're doing, just switching them. Okay, so I'm gonna move this to the side here so that you can see a little bit better, I hope. Okay, so here it is. So column 1, just change the column to row 1. Column 2, row 2. Column 3, row 3. So that's what T stands for, is transpose. Transpose means change the column to row. Change the column to row. Change the column to row. Again, column 1, row 1. Column 2, row 2. Column 3, row 3. Okay, so that's what QT stands for. And the rest is just multiply matrices. So here is QT, which is being transposed. This is the original matrix. And make sure follow the rule of multiplying matrices, that these two numbers should be the same. This number and this number should be the same, then you can multiply. So I have three rows, 4 columns, 4 rows, and 3. Okay, so 4 rows and 3 columns. Okay, so make sure that this number and this number are the same using multiplication matrices rule. Again, to multiply matrices, this number here and this number must be the same. So this this matrix QT has 3 rows, 4 columns. This matrix has 4 rows and 3 columns. Then you can multiply. This number and this number should be the same. And all you have to do is just multiply. So row times column. One more time. Row times column. And I'm going to write 2 square root 5 down here just to make things a little bit faster. So 3 times 3 gives me this 9. 1 times 1 gives me this 1. -1 times this -1 gives me this +1. 3 times 3 gives me this 9. Add them up gives me 20. Simplify it gives me 10 square root 5. Where did I get this 10 square root 5? Row multiply column. And repeat that all the way through. And I'm going to shortcut this so that we save some time. So here is our matrix R. Okay, so one more time. Where did I get these values? Right here. And same thing, 0, 0, 0. All I do is row times column gives me this guy. Row times this column gives me this one. Row times this column gives me this one. And the rest is just the same procedure. Here I write down the calculations for this part only right here. So this calculation right here is this row, this column, add them up, simplify, and gives me 10 square root 5. Repeat that process for all of this entry right here, all of this right here. So this is my R. So I have my Q. So I have a Q already. So here's my Q. Here's my Q. And here's my R. Now multiply. So again, check if it's true or not. So here's my Q. Here's my R that I found out from factorizations. Again, when you multiply matrices, make sure that this number here and this number here are the same. Then you can multiply matrices. So row times column, which gives me back to this 3. Row times this column gives me this -5. Row times the third column gives me this 1. Repeat that all the way through for every one of these entries. So second row, second row, first column will gives me this 1. Second row, second column gives me this 1. Second row, third column gives me this 1, and so on. Third row, first column gives me this -1, and all the way through, and it does come back to the original A matrix. So therefore, our orthogonal basis, which I have here, is the true answer, the real solutions that will give us back to the original A. Okay, so that's what we need to do for part 2, is we have to show that the orthogonal basis is the real solutions for the original A matrix from the beginning that I have. Okay, so how do I do that? I have to normalize each of these vectors. After that, I can find my Q, use the Q, transpose the Q. Transpose mean column to row. Okay, write the column as row, which I have here. So here's my column. All right, here's my column. All right, so QT means this is my Q. QT means column, write it as row. Column, write it as row. Column, write it as row. Okay, so that's what QT stands for. First column become first row. Second column, second row. Third column, third row. That's it. And once you do that, bring the A back, multiply the matrices, and that will come to my R. So now I have my Q, I have my Q, I have my R, multiply column to row, that comes out to be this 3, and so on all the way through. I'm going to skip all those process, so it does come back to the original matrix A. So therefore, this orthogonal basis V1, V2, V3 is the solution to the matrix A.